So, um, the way we describe analog is to Verilog, so be it behavioral or structural, and we plug in a couple analog functions that we call auxiliary cells. I highlighted them here in blue. So basically, it can be either a buffer, analog buffer, can be a header cell, a switch, a flying cap, a comparator. So usually it's a 12 transistor below block that you can easily lay out and plug in into your digital flow. I have added circuit diagrams of legacy designs we have published in ISSCC, CICC, or VLSI, which are flagship conferences in circuits. So these are from our groups. These are SAR DCs, step sensors, digital LDOs, PLLs, DC-DC converters, and the list is really long. So these are just to show you what type of block we made. Okay. All right. So these are the auxiliary cells. They are, as I said, they are really small, limited number of transistors. And why we do that is because we can do a lot of iterations. We can design different versions with different sizing of the transistors, and we can just plug them in the generator. So, and then the flow is really automated. But then after some work through the DARPA program and CHIPS Alliance, we started working with Align, which is very, very amenable to generate this layout. So if you give to Align a design that has 12 transistors or 5 transistors, it's basically going to do a decent job that you can actually just take the layout and plug it in your flow. So that's what we have been doing. It's not as easy as it sounds. You have to make constraint file, but it works. And we have done that with a couple designs. I'll get to that later in this presentation. FASOC, which is the original flow, is a set of relies on a set of proprietary tools, the traditional ones: Synopsys, Cadence, Calibre, HSpice, and Spectre. But now, as the open source initiative or movement started, there's a bunch of tools that we can use now. For synthesis, we can use Yosys, ABC. We added the Sherlog and UHDM plugins for system Verilog that was developed by Ant Macro and Google. We are using OpenRoad. We are part of it. We are using Magic and NetGen for DRC and LBS and Klayout as well, which is a pretty cool tool. And then we use ngSpice and Xice. So we have the whole tool chain in SkyWater 130. We taped out a couple of chips. I'll get to that later. But we also used some of these tools to tape out in GF12. And right now we're actually taping out in Intel 16. So this is growing really fast over the past 2 years. We started with Google like 2 years ago. And now we can see that a lot of things are working. So now, since we've looked at the Open FASOC framework and how to leverage the digital flow to perform the analog layout generation step, in the next slide, I'll try to explain a little more what are the trade-offs and examples of how this is done. I really like this diagram because it summarizes where FASOC, which uses the commercial tools, is today or has been. So if we take a full custom layout, which is all the way to the left with 100% complexity, and compare it with the initial version of FASOC 1.0, which started 4 years ago, which uses minimum constraints without any custom placement or anything in APR tools, then obviously the complexity goes way down. However, we can see that the performance takes a hit compared to high-end analog design. Now, when we swing back into the middle, where we use partial constraints and digital compensation to address non-idealities, this still reduces complexity a lot compared to fully custom flows and tools. And we gain back a lot of the lost performance in loosely constrained approach. So we kind of get the best of both worlds. In fact, in using our cell-based digital approach, we are in reality avoiding the extreme complexity of trying to take in all the PDK DRC rules that comes in with full custom automated layout, like routing or active layer drawing, etc. Also, with the rule of diminishing returns, the time required porting to a new PDK or even in a new design topology would essentially make an automated full custom analog generator too costly to make across PDKs and test cases. So I think we have here a sweet point, which I fundamentally believe we could push a little more to the left, closer to the full custom layout, using the open source tools. And the reason is because the open source tools, we can see more software people adopting these tools, and they are using new routines, APIs that now I can use, or I can just use a different methodology to do design. So that was really exciting to see, and I'll show you how we evolved from being a cell-based approach using digital design to including more APIs and routines to do more custom layout. Here's a few examples of what constraints look like. This is a PLL, DCO for a PLL. It's the most sensitive block. We use a Python script to just place the fine cells and coarse cells in a structured manner. So this helps a lot. You can get back a lot of the performance of a PLL. And this only uses place and route tools for digital design. Another example, which is interesting here, is for power regulation. It's a digital LDO. We taped out in different technologies: SkyWater 130, 65, LP, and GF12. You can see that the pre-PEC simulation looks smooth and with the max load current and the array size. But then when we do place and route with unpredictable placement, it leads to more variations, and we get our max load current reduces versus the array size as we increase the array size. So this is a problem, and we had to resolve it. There's also limitation regarding the the narrow routing due to the digital flow. The router is actually just going to route it like a digital design, so that's not great for an LDO specifically. But then after coming up with a more structured placement of the switch array, as well as fencing of some of the cells, you can see it there on the bottom right. We also did automatic PDK parsing of its metal stack info to calculate resistivity over the power stripes mesh. We can see then that the performance is considerably improved with the smooth curve that we've seen before in pre-spec simulation. So that's a post-spec simulation. So this type of tweaks here to the digital flow really get us to closer to the traditional layout. Yeah, so now I want to mention a little bit some of the open source IC contribution we've done. We have been at the forefront of these open source tools with UCSD, working on OpenRoad, but we also worked on different tape out and getting the flow and frameworks in the community, which was really great to see over this past 2 years or 2 years and a half. So we started really easily at the beginning. We started with the temp sensor, which is a small block. We just made an array of them, 64. We wanted to explore the VTs of this technology. And we taped out a small LDO. This was done with one student for your information. So this shows you how powerful it is to use our framework and tape out this bunch of circuit here or temp sensors with different sizing and different flavors that allows you to do design space exploration really easily. So this was integrated in the harness. If you notice here, we have our own harness in the middle. And the reason is we didn't trust really at the beginning the harness from eFabless because we noticed there was some hold violations. And since we were part of OpenRoad, we kind of anticipated this issue. So in this MPW1, we were the first people to get silicon working, which was really exciting for us. So a couple of months later, we got the chips back. So we tested everything. We automated the testing. These are 64 sensors. If you've ever tested the temp sensor, you have to test it over steps of 28 degrees C or even 10 degrees C. You can see that you can see the result on the right. So you have to do calibration and all. So it's not an easy task. So we have to do a lot of Python scripting and data parsing and all, or file parsing to do this work in a more efficient way. But then the cool thing about this is we use different flavors, right? So you can see that when we use the high-speed sensor, we get a little larger design, but then with high density flavor transistors, we get a denser temp sensor. And then on the left, we can see this design space exploration. This is really interesting for, companies like, global foundries where they want to know how their process is doing. So you can just, tape out an array of these sensors and you get a really cool, idea of where, what are the sweet points of your technology here. So, yeah, so then we did much more measurements. We are in a below 1 degree C temp sensor. This is really state of the art and was published in the solid state circuit letters recently. So this is one of the first open source, really fully open source tools or open source framework design with silicon results. This is a comparison table. You see always this in this type of tables in circuit conferences. We compare to JSSCC, CICC, or ISSCC papers. We can improve the design. We actually taped out version 2 and version 3. So this shows you that the way in the open source world, it's a more iterative approach, right? The first version was really cranking up the design and put it down on silicon. But then on second version, we started playing with the flow and improving the design, improving the tools. So I'll get to that in the next slides. So on the next shuttle, MPW2, we tried to step up our game. In Michigan, we do low power design for IoT. That's what our group originally is doing. So we like to bring down the power envelope, right? So what we taped out is a root of trust called OpenTitan. It's also an open source root of trust. It's pretty, we had to do some hack to get the design to work, but it's we got it finally to work. We still have to include some of the blocks, like for encryption and all, and we're working on it right now on Intel 16. But the idea here is that we were able to do another array of analog blocks, which is the digital LDO. There's 10 of them there with different loads, different circuit features. We added some voltage references and analog buffers, and we have and we actually connected to the LDO to the core or the root of trust to basically show the first AMS SoC in the open source world. We also worked with one of my students to make an ECO flow to fix hold timing, because this is a real issue in the open source world. OpenRCX, which is the RC estimator in this tool chain, it still needs some work. So at that point, or in MPW2, which is 2 years ago, so we had to do some heuristic loop. I'll get to that next slide. But this is what I want to show here is that these open source tools were in a very, very early stage, right? So we started developing tools like routing, non-default routing for the temp sensor to connect. It's basically a special route to connect the header cells to the power ring. You can see it there. Also, we wanted to increase the routing width, and also that was useful. The other cool thing we did is we started using much more Python to structure the placement of the power switches. We included a VREF inside the digital LDO, and we taped out a couple of them. Yeah, this is just a summary of the root of trust. We are still missing some of the blocks. So I heard from the previous talk that there was some work on root of trust. So if there's available Verilog we can use, that would be great, because we are not supposed to do the Verilog, but we use it to do a demonstrator. So I just wanted to add that here. We also taped out a new version here. This is MPW6. This was using Pulpino, but we want to, we just wanted to explore how that platform is. And we were able to push a little bit the PPA using OpenRoad, basically density and speed. So this again shows you the iterative approach of open source design. This is the ECO heuristic loop. The idea is, okay, we get our design, we get hold violations. How do we fix them? The tool doesn't converge, or at least at the time it didn't converge. Or if it converges, it gives you a really, really bad setup. So what we did is really simple. We just took the design, hacked the flow, added the heuristic loop there, added buffers at the end of the input flip-flop or start flip-flop starting point. And we started including buffers in a heuristic loop there, and we were able to fix the whole violation. So it's pretty simple, but it's a very educational approach, because students can start playing in the tools, right? And they start understanding why the router is not doing this, or why do we have hold violation. So I thought this was exciting. Another thing that is really cool here is that in these open source tools, the code is auditable. You can go, if you want to make something or some funky design, or if you have a research idea you want to do, like stack voltage domains or buried PD engine. So you can go in the code, check if you're proficient in coding, and update some of the functions. So that's what we did. We are not EDA people originally. We did some EDA tooling, but we work more on circuits. So we started looking at the code, and we noticed that we can do much more playing with these tools here and these functions that are available online with documentation. And we started updating them and adding voltage domains. And now there's this UPF flow, a simple flow that anyone can use. So Peter Gatford from the Army has taped out the chip with voltage domain and power switches, which in Intel 16, using some of these open source tools. So this is really great to see, and we're going to see much more of it in the future. Yeah, so this is another exciting project we had during summer 2021. We taped out the root of trust in GF12 using OpenRoad. So we don't have a full open source tool chain in GF12, but we used what was available, and we were able to get a 350 megahertz IBEX-based core at nominal condition. but it's pretty good. And that's the sensor actually, which is fully open source and using a whole open source tool chain, is actually below, it's around 0.2 in accuracy, which is really great for specs. So we never got to test the chip yet because we got the chips back late, but we're after the Intel 16 tape out, I'll get to that. Right, so this was about some of the open source tape outs. We did much more of them. I just don't want to take too much time here. Some of them are not published, so we have to be careful there. But some of the cool projects that came up early this year is the collaboration with NIST on doing test structures for cryogenic temperature modeling. So this is really cool because these quantum systems or computers, they need a quantum control system, right, or calibration system. So originally, the control system was imagined to be running at 300 Kelvin, but that's not ideal because you have to be talking to a quantum processor that's running at 20 millikelvin. So it's really low temperature. So the idea there is that you have to create models so that you can design at 4 Kelvin, so you can interface with the quantum processor. So that's the idea here. This is just a cool picture showing you the gradient of temperature on where everything needs to sit. But basically, we started working with Brian Hoskin from NIST and Tim Ansel from Google. We started working under the umbrella, and we said, hey, we need to make these structures and make so we can create models at cryogenic temperatures. So everyone here in maybe 6 months can start and design their chips at this low temperature. So this was the first tape out we did. I'll go a little more detail. There's really simple structures from almost gap arrays, precision resistors, line resistance, VR resistance, etc. So all of this is needed so you can create this in 4 or 5 models, right? So this was taped out in PW5, but the cool thing there is that we started playing with these tools, open source tools. I had a really smart student who started playing with OpenRoad, and he's doing depth manipulation with Python because we need an interleaved placement of the inverters, right? So it's kind of painful to do, and you end up doing it manually. So what he did is created a routine in Python that goes and changes the placement of the inverters, and then you provide it to OpenRoad, and it's going to do the routing. We started doing regioning, so you can see that the dividers are on the right there, so and placed separately. So these are very, very useful techniques for physical design. So we taped out actually 24 versions of this, all the available standard cell libraries. So we use those. That's useful for process monitoring or centering and all of that. We also started using something called GDS Factory. This tool, this is really interesting. So the GDS Factory is a tool that is supposed to be working for photonics, right? We noticed that in photonics, they have a lot of routing with different formats. So we just looked at it and say, hey, we can use some of it, right? So this VR resistance, they are like, you know, snake shape. So we started using some of the routines that they already had and plugged them in Skywater 130 and just reused them to do this tape out. So we got all of this is automated right now, all these meshes and all. And even more, this is the MIMCAP array, right? So what we made is a simple function that takes the layers, pitch, dimensions as an input, and it dumps this, right? So then we use that function, we provide it with a different P cell, and we can generate a diode array. We can generate flying caps for the DC-DC converter, and the list is long. So this function is actually used by different generators in our framework. The same function is actually using the array that was generated is in a recursive manner to generate the paths and connect everything together. The routing is called, for routing, you have to run a different routine, but this is how we can reuse or recycle the code available in the community to do much more advanced design or more custom design. Yeah, so this is an example. We have the MIM arrays and the diode arrays. And we ended up doing reusing some of the functions, and this was done in we started to tape out end of December and finished it like in February. And the result, this is the resultant test die. This is like 1400 pads for 400 transistors. So, and the list is there. Basically, this is really great because you can see the power of automating everything. This would have taken 6 months in an industry. And this is with NIST, so they actually just see what is the quality, because they are gonna be testing it. So it sounds like they were pretty happy about it. And this was done by a grad student. I think it's great. So anyway, this was, we did multiple tape outs. The cadence is every 3 months. So we did MPW5, MPW6, and MPW7. Just from the geometries here, you can see that things are getting much more complex, and we're still getting the cadence of taping out every 3 months. I don't know. I'm, you know, it's pretty exciting to see that, because it shows you in a way how automated analog design is working here, and it's getting you the final result. So in the final test die, we have BCOs, inductors, which are painful to design, photodiode array with access transistors, TIAs and OTAs, and ReRAM bridges. This is another interesting project. A high school student reached out to me from Maryland. Apparently he's very smart. And he told me, hey, I want to work on your framework since it's open source. There's a GitHub link. He checked it and he was but then he insisted. He sent me his design. I reviewed it. I found it was really good. This is his design. If I told you this was done by a real engineer, you would have believed me. So this was done by a 17 years old from Maryland. He's not even in Michigan. He taped out at 10 gigahertz and 2.4 gigahertz. He did all the flow, and he pushed this to GitHub. His name is Ryan Wands. Pretty smart guy. So I already wrote a letter of recommendation for him for his college applications. So yeah, so this is cool to see. NIST is so this is the project with NIST, and the tape out was done by a 17 years old. I think it's great, and we'll see much more of this. I'll just end up here with the talk about OpenFA. This is the framework. The initial framework is using OpenRoad and the digital flow. It's getting much more complex, not in a bad way, but in a way it tells you that you can do much more by using the Python APIs we're using. If we make a database, we can actually just call this routine. So there's discussions in including this in OpenRoad or maybe GDS Factory. But the idea is maybe having a disruptive way of doing analog or custom IC design. So now back to my figure that I like. I have to make a better one, but I really like the idea here of having the 100% constraint versus the loosely constrained. So with our approach here, with increased automation and with the open source movement that is happening, we can see that our design are getting much more complex and much more customized. And we're actually getting back some of the PPA we're losing when we use a cell-based approach that only relies on the digital flow. So this was my talk about OpenFA SOC. I would like to mention a little bit some of the work we're doing in SSCS, Solid State Circuit Society, with Boris Merman. So there's a couple of things happening right now. There's a Chipathon that goes through 6 months. There's people from all over the world doing some design. I'll give you more detail there. But there's also a competition that's actually right now active. So if there's any students here, they should go to this link here and maybe make a notebook of some of the work they did through the master's or undergrad and send a pull request to that GitHub. And they will get a travel grant to come to ISSCC 2023, and maybe they'll get a prize. But this is a low-hanging fruit for students. So please share with your students or people who this is open to everyone. Actually, you don't have to be a student. So yeah, so this is, I'm part of the technical committee for the open source ecosystem. This was created last year. And this was a result of the open source movement or initiative by Skywater and Google and eFabless. And the SSES want to ride this wave and get more people to join the solid state and IEEE community. So this was one of these really catalyzing event. I mean, the open sourcing the Skywater 130, and there was a lot of people who just jumped on this. It was an immediate success in terms of attracting people to submit their designs and to MPWs funded by Google. In our case, we are actually using the commercial shuttle by eFabless. It's called ChipIgnite, and we get some funding through Chips Alliance and other or SSCS, and we actually run this Chipathon. So we are looking for funding for next year. I mean, the Solid State Circuit Society to keep this Chipathon going. There's people interested to fund us, but if you guys know more people, that would be really helpful. But how does this work, right? Oh, wait, this is a website, so please go take a look at there. There's multiple links so to understand what's happening. But really the basic idea here is to say, okay, we are going to hop on the same shuttle with, from Google and eFabless, and basically get some of that support, pay some of these harnesses. They cost around 10K. In GF 180, it's going to be around 5K maybe, or 3K, so it's even more cheaper. And we offer to people from all over the world the opportunity to submit a proposal. The bar is really, it's not high actually, and you can tape out a chip using these harnesses. So a lot of people around the world doesn't have access to silicon. And this is great to see. So we had a team from the US, from Purdue, this is 2021. We had people from Vietnam, Pakistan, India, Argentina, and it's all over the place. So this is a map of all the countries. There's 18 team. We got 61 design proposals. We just selected 18. We refused some of them because they weren't possible. You can't tape out, your tape out can't be SerDes as a first project, right? So these projects were canceled or restructured for the next Chipathon. And at the end, after 6 months of work, we have a weekly with these people. There's 100 people showing up from all over the place, and we ended up taping out 11 of this chip. We offer to the winners or the people who taped out, we offer them an IEEE a membership and SSCS membership. And we still want to do some work in Europe. You can see that in 2021, there was none. I think it's better in 2022, but we're doing some, we are reaching out to people from all over the place to have them work on this. And we can see that we're creating a huge library of IPs that other people can recycle. It's on GitHub. You can just pick it up, use it for the next shuttle. So this is the way we want to do chip design in the future, which is really disruptive. Here's a quick look of what was taped out. So one of the new, okay, so I'll go fast. I thought I had more time. No, it's all right. So these are the, no, it's all right. I'll go fast. So these are the projects that were taped out. You can just go to the list. I'll share the slides. And this is the 2022 Chipathon. We have much more people, different projects. You can see we have Europe there. China is not present for some reason, maybe because they don't have YouTube, but hopefully we'll fix that. But this is our committee. Boris Merman from Stanford is the chairman. We have different people. We are looking for people to join this community that are interested in open source and research and education. So please reach out if you're interested. And I'll end here my talk. Sorry about that.